rest during the long weekend. We finished grading of your midterm exam. You probably already see the grade I posted yesterday. That's the distribution right now. After the regrade period, our statistics might shift a little bit. Like right now, it's shifted up a little bit. Judging by the mean, it shifted up by like 3 or 4 points. Nevertheless, we're doing much better than midterm 1, and the regrade request is still open. I also posted a similar style of the survey regarding like how things are working. So please do fill out those survey to give me an idea in how we can improve for the last 2 weeks of the quarter. And if you have questions for the midterm exam, I also posted a walkthrough video for midterm 2 exam. Please watch it, and if you see any problems you want to explain, you think you deserve more partial credit, remember everyone got 4 regrade request possibilities. Basically, you regrade request just like you submit and tell me like what you think is going on and why do you think you deserve more points. And what your grader will do is will look at your answer again. It may work for you or against you. It basically depends on what your result, what your answer is. Okay, and that's the general administrative announcement. Any questions so far? Nope, we're good. Okay. And one more thing, I would just want to clarify before we move on. I think in my buffer lecture, I made a mistake. So when we're looking at these plots, for example, plotting Gibbs free energy versus time, right? We see that this is going to be a down process, and that's where equilibrium is. And this plot is true for closed system, constant, temperature and pressure. I think in my buffer lecture, I said it wrong to be isolated system. It should be closed system. I want to make sure we correct that before we move on to our final exam. Okay. Anything else before we start our today's lecture? Yes. Yeah, that works the same way. So the question is, does Helmholtz free energy works? It's basically the same idea, replacing G with A. It's closed system, constant TB.
The only one that was isolated was entropy, right?
Yes, the entropy figure is isolated system, and no additional conditions. Okay, so back to our finishing part for our chapter 5. So as a quick summary and refresh your memory on chapter 5, what we did is we started talking about the standard heat of formation of a substance. We went over a careful derivation in how does that standard heat of formation is being measured and calculated using calorimetry. And then we went over in application of using the appendix table to calculate the heat of the reaction. Now, in the previous lecture, we also went over a discussion of conventional entropy, right? The same idea. How is conventional entropy being defined? How people measure conventional entropy? And this is the last bit, which is how to use the appendix table to calculate standard entropy or standard conventional entropy of a reaction. Right, so here's the general format of our chemical reaction. So what we have stoichiometric coefficient. So this little mu here, it's negative for reactant, positive for product. We're moving everything to the right-hand side. A and B, these represent the specific chemical species involved in that reaction. So the standard entropy change of the reaction, or delta S of the reaction at a certain temperature, we can write it as delta S. Normally, we would put a T here. So this temperature may be 298 Kelvin, maybe some other temperature, but we typically will specify a temperature. And it's not here, such as that's the standard state or 1 bar pressure. So the standard entropy change of the reaction is, again, the sum. And then you have our stoichiometric coefficients. Then the conventional standard molar entropy of each species involved in the reaction. Right, so in this equation, it's important to know what exactly are we talking about. Like here, this is the entropy change, standard entropy change of the reaction. This dot means like P equals to 1 bar. T means at specific temperature T. On the right-hand side, what we have, this is the stoichiometric coefficient. And this one is our standard conventional entropy, molar conventional entropy. And again, this M is for molar. T is specify what temperature it is. I tells you which chemical species it is. Right, so this is the number we'll be able to find when we're surveying the appendix table. Also, this is the number that we will be able to calculate if we give you enough information. Right, so to make a link, right? So this is the long derivation. Remember, in this case, we did the long derivation to find out the standard molar conventional entropy of SO2, the very long derivation before our midterm 2 exam. And then these number will later on be archived in our appendix table. So when we're using the appendix table in this question, for example, it says use the data in appendix to find delta S naught 298. So this is telling you you are supposed to find the standard entropy change of the reaction. So the reaction of interest here is 4 ammonia gas plus 3 oxygen gas go to 2 nitrogen gas and 6 water. Right. So for this question, the way we're gonna solve it is to, well, first of all, write out the expression. We're looking at delta S naught 298 equals to the sum of my stoichiometric coefficient times the standard molar conventional entropy of each species. Or effectively, what are we looking for here? We have -4, so that's for ammonia, and times the standard molar entropy of ammonia. Let's see where that is. Right, so that's here. The number is 192.45. And then for my oxygen, that's -3 times the standard molar entropy for oxygen, O2. That's this one, 205.138. And plus my product, so 2 times my N2, which is here. It's 191.61. And plus my 6 water. H2O, we are looking at H2O liquid. So here's one of those examples, like you want to keep an eye on the face of your substrate, right? Whether it's liquid or gas, you might get different number from the thermodynamic table. So in this case, we're looking at liquid water specifically. So the number we're using is a 69.91. And you plug in the number to solve for the final reaction. And this one, if we solve it, that's negative 582.53 joule per mole per Kelvin. Right, and if you think about it, once we get this number, it's always nice to do a very quick sanity check. So when we have reactions involving gas molecules, we know that the entropy of gas molecules are way larger comparing to the entropy of your liquid and solid, right? Because your gas molecules has way more possibilities in moving in the space. So in this reaction, we started from 7 gas molecules. We end up to have 2 gas molecules in my product. So in this whole process, we are expecting the delta S of the reaction to be a very negative number. And indeed, we get a very negative delta S of the reaction. So I call this a nice like sanity check to make sure you get the sign correct. Yes?
So is the delta S of the reaction, could it be thought of similarly as like the delta S of the system?
Yes and no. So your reaction happens in this. Remember, the thermodynamic system is defined to be the part of the universe that we care about. Now, if the system, there's a reaction going on in the system, right? So that's the best way to describe it. It's a little bit risky to say the reaction is a thermodynamic system. What we can say is there's a chemical reaction taking place in the system of interest. All right, so this part is, again, just to finishing up what we discussed, that is how to use the appendix table to calculate the entropy change of the reaction. And as a final note, we went over to discuss our standard Gibbs energy or Gibbs free energy of the reaction. Now, in this one, it now becomes very obvious. We went over these 2 discussions, right? The delta H of the reaction is the sum of the stoichiometric coefficient times the molar enthalpy of each species. The conventional standard entropy of the reaction is the sum of stoichiometric coefficient times the molar conventional entropy of each species. What else do we know? We also have our definition of Gibbs free energy, so G equals to H minus Ts. So there are 2 different ways, 2 different things we can calculate here. First of all, when we're looking at the standard Gibbs free energy of the reaction, we can write the same way, delta G naught of the reaction. So this T, again, specifies the temperature where that reaction is taking place. You can get it from our thermodynamic table. Right, so that's just a sum of stoichiometric coefficient times the molar Gibbs free energy of that specific chemical species at certain temperature. And the other question is, well, where that number comes from. What does that delta G of the Gibbs free energy of formation in our appendix table come from, right? So that's this number here, the delta F G naught 298. So this can be calculated by coming from the delta heat of formation, G naught, at certain temperature for chemical species I. That equals to the H, the enthalpy, the heat of formation, minus temperature times the conventional entropy of formation. Or let's do an example question here. So what we just said is basically saying you have 2 different ways to solve for the same problem, or the Gibbs free energy of the reaction. You can either use the table directly by summing up the stoichiometric coefficient times the delta G of formation in the table. Or we can use G equals to H minus Ts to calculate the delta G for the reaction. So if we use this reaction here, which is the formation reaction of magnesium oxide, and you want to say compare that with the listed value. So what does it mean? So we can first calculate my heat of formation of MgO and also the standard molar entropy of magnesium oxide. Right, so the heat of formation of my magnesium oxide, so that one you can read from the table. And then for our delta S of the reaction, again, that's the sum of our each of the species involved. So note that in here, my magnesium and my oxygen, both of them, they are in their elementary form, but they still have a standard molar conventional entropy. Right? Its heat of formation is 0 when we're in its elementary form, but the standard entropy or the standard conventional entropy is never 0. So in this case, when we're calculating the entropy of formation of my magnesium oxide, what we're looking at is the delta S of the formation reaction here. So we want to write the formation reaction and use the formation reaction to solve for the delta S formation of this species. Or the other way to put it is we're looking at Sm of your magnesium oxide condensed minus S0 M of my magnesium condensed minus 1/2 of my Sm oxygen in gas form. Right, so plugging the numbers, we get our final number to be negative 108.31 joule per mole per Kelvin. And what the question is asking for is the delta G, the Gibbs free energy of formation of the magnesium oxide. So we have delta G naught 298 of magnesium oxide. That equals to H minus Ts. So H is this one. This one is in kilojoule per mole. And then minus Ts, right? So my temperature is 298 Kelvin. So that's my temperature. And my S entropy is negative 108.31. Note that here the unit is joule, so we want to divide it by 1,000 to make it kilojoule per mole. Here the temperature and temperature cancel out. Right, so this is one example that basically using the appendix data, you have different ways to calculate the Gibbs free energy of a certain species and the Gibbs free energy of the reaction. Okay, so that's the end of our entire chapter 5. So chapter 5 is basically focusing on our appendix table. Right, so we are trying to use what we learned in thermodynamics to say like, hey, what are these things that we care about? Right, how does my heat of formation being defined? How do we use the thermodynamic table to calculate properties that we care about when we have a chemical reaction going on? So the entire chapter 5 is related to the derivation and the use of the appendix table. All right, do we have any questions before we move on to our chapter 6? Nope, okay. Let's see, chapter 6. All right, so now we're moving on to finally one of the questions I always get when we're looking at people's comment is, why do we care about thermodynamics? Why do we care about all these derivations, right? So here we're eventually approaching how to use thermodynamics as a chemist to predict things that we care. Like in this case, we're trying to say like, now we have an ideal gas reaction mixture, right? What's gonna happen if I change the pressure? What's going to happen if I change the temperature? What's going to happen if I add an inert gas into my reaction mixture, right? How to predict the movement of equilibrium. Will we be able to push the reaction towards the forward direction or the backward direction, right? So basically the idea here is how to use thermodynamics or how to build a link between thermodynamic functions like chemical potential with a chemical reaction equilibrium. So today, hopefully, we will be able to finish 6.1, 6.2. I'll see how far I go with 6.3. So the goal here is to first introduce ideal gas mixture. We'll simplify our life by only looking at ideal gas reactions at the moment. We'll first introduce what is ideal gas mixture, refresh your memory on chemical potential of the ideal gas mixture, one phase. And then we'll talk about ideal gas reaction equilibrium by defining the reaction equilibrium constant and see one example together in how to use thermodynamics to solve for reaction equilibrium constant or vice versa. So let's get started. First thing, chemical potential in equilibrium mixture. What do we have here? Again, effectively, we did all these derivation. At the end of the day, we want to able to link our derivation into something we can measure. So in this case, at the beginning, let's think about what is the chemical potential of a pure ideal gas. And then we'll define what does a ideal gas mixture or what's the definition of an ideal gas mixture. And then we'll see what's going to happen when we have reactions between different ideal gases. So getting started, this part should be a review when we're talking about chemical potential of a pure ideal gas, right? So pure ideal gas, what does it mean? So a few things. First of all, we know it is an ideal gas, so we can use PV equals to nRT. And remember, we have our full definition for chemical potential. So chemical potential for species I in equals to the partial differential of Gibbs free energy of everything in that phase alpha divided by the Ni of alpha at constant pressure, temperature, and everything else kept constant. All right. So in this process, there are several things that we know by only looking at the nature of chemical potential. So first of all, chemical potential itself is an intensive property. So looking at our ideal gas law, we have pressure, volume, number of mole, and temperature, right? So we have 4 different things in my ideal gas law. So since my number of mole and volume are both extensive functions, my chemical potential, the nature of my chemical potential is an intensive function. As a result, what we can say is we can write the chemical potential as a function of pressure and temperature, just because it is an intensive property. So that's the first piece of information. All right. What about the next one? The next one is we want to use our understanding of the chemical potential of a pure substance. So in this case, in the original definition, alpha means we have different phases. I means we have different chemical species. So when we have a pure substance, this equation effectively is simplified for this pure substance, one phase, to be mu equals to dg over dn at constant Tp. Right? We only have one species. We only have one phases. That's why we can do the simplification. One phase right. So for pure substances, one phases, we can write that my chemical potential equals to my molar Gibbs free energy. And using my Gibbs equation, we know my dg equals to negative SDT plus VdP. Or the other way to put it, we can write our change or infinitesimal change of my chemical potential equals to the Gm, the infinitesimal change of my molar Gibbs free energy, equals to negative Sm dt plus Vm dp. All right. And then we want to focus on our standard state. Okay, so bear with me a little bit. So thinking about what's going to happen for a chemical reaction that's not at a standard state. So now thinking about the process that we only have isothermal processes. So when we have the temperature kept the same, what's going to happen? So for isothermal processes, we end up getting d mu equals to Vm dp, and since we have PVm equals to RT for ideal gases, this change of chemical potential becomes RT over P dP. Or if we're looking at the isothermal processes or the change of chemical potential, when you have species in different pressure, or the other way to put it, you can have chemical potential of temperature and P final minus the chemical potential of temperature P initial. What that gives you is the integral of this RT over P dP, or RT log P final over P initial for ideal gases. Or the other way to put it, if we plot my chemical potential versus the pressure change, before we do that, we want to say, what is my reference point, right? So here we have PF and P initial. Let's say my P initial is my standard state, where my mu naught is defined to be pressure at 1 bar. We can then define the chemical potential at certain given temperature and any pressure with this mu naught T. So we're replacing this term here with P naught. So the standard chemical potential plus the difference between the two pressure. Or if we plot what we want, like in here on the y-axis, that's the chemical potential at any pressure, and specified temperature, minus your standard chemical potential. So this plot versus the P over P naught will be a logarithm plot. All right, so how to read this figure? So if you think about it, what do we have here? So when we look at this process, this part, right? So this part, we're talking about my pressure over P naught approaching 0. Or the other way to put it is we want to reduce my pressure so it's infinitesimally small. So when pressure is almost 0, what does it actually mean? Right, so we see that the mu minus mu naught is a very small number or approaching negative infinity. So what does it mean? So in this case, when pressure approaches 0, we have volume approaches infinity for this gas. When volume is approaching infinity, my entropy of the system is also approaching infinity. And using my chemical potential, mu equals to Gm equals to Hm minus T Sm, right? So that's a definition of my Gibbs free energy, G equals to H minus Ts. Now, for ideal gases, my enthalpy is independent from pressure. It's only a function of temperature. Temperature is something defined as a positive number. We know Sm is approaching negative infinity. Sm is approaching infinity, so my chemical potential is thus approaching negative infinity. Or the other way to put it is, what does it actually mean? Well, we have the chemical potential approaches negative infinity. So remember, when we talk about chemical potential in phase equilibrium, we say that chemical potential is the intensive property that tells you what is the direction of my material flow, right? So for material equilibrium, my material or my chemical species always go from a higher chemical potential side to a lower chemical potential side. That's a quick review. So what does it mean? It means like when our pressure is approaching 0, my material always flows in to that phase. So like in this case, if you have like, imagine you have 2 chambers, one at a lower pressure, one at a higher pressure, right? So when you mix these 2 chambers together, obviously the gas or the material will flow from a higher pressure one to the lower pressure one. And the nature behind that obvious observation is governed by the chemical potential. I hope it makes a little bit more sense. So I'm trying to give you a little bit more idea, like what is behind all these numbers and equations. So in this case, what do we have? We imagine you have 2 chambers of ideal gases. One has lower pressure, one has higher pressure. So when we mix it, the gas always flows from the higher pressure one to the lower pressure one. And the nature behind it is the chemical potential driving that material flow. All right. Any questions? Okay. Now, that's a quick review on chemical potential, and I hope I'll keep talking about chemical potential. I know this is one of those abstract concepts that when we first define it, it will be like, hey, why do I care about it? It's so complicated. And I want to give you more insight in why do we actually care about it? How does it link to our actual like real-world applications? Next one. So before we talk about chemical equilibrium, we want to first give our chemical potential of the ideal gas mixture. We want to give our ideal gas mixture a more firm and accurate definition. So when we define an ideal gas mixture, what we're talking about is a few things. First one, we know that our ideal gas law, we want it to be still hold true. This is very small. Or you still have PV equals to nRT. Now, instead of a pure substance, now we have N total. So this N total set, for example, if I have like A, B, and C, right? So my N total will equals to NA plus NB plus NC. Very straightforward. The next one is a little bit more abstract. So the next one that says at equilibrium, well, we have an ideal gas mixture at equilibrium. What we're saying is that the partial pressure of any species I, or we abbreviate it as PI, which is a partial pressure of my species A, B, and C, will satisfy that PI star equals to, well, satisfy this one. Well, we have the partial pressure of my species I equals to the mole fraction of my species I times the total pressure. So if my total pressure is 1 atm, and the mole fraction of my A, B, and C are each equal to 1/3, so the partial pressure of my A, B, and C will all be 1/3 of the total pressure. So that's another criteria for our ideal gas mixture. All right, so 2 things. First thing, we have ideal gas law. And second thing is we have our partial pressure of different species in the ideal gas mixture. And what does it mean? How do we use our definition of the ideal gas mixture when we're talking about chemical potential? So that goes to this part. So when we're looking at chemical potential of this gas I in the mixture at temperature T, and we know that PI star. So this star denotes that's the partial pressure of the pure substance I. So in here, we can rewrite the chemical potential of my ideal gas mixture for species I, that equals to my chemical potential of my pure species I at certain temperature as a function of partial, the mole fraction times pressure, or that's effectively the same as writing that to be mu I star T Pi. So only for ideal gas mixtures, we can write the chemical potential of a substance in a mixture to be equal to the chemical potential of that pure substance at that partial pressure. All right, so for example, in this case, we have A, B, and C, right? That's the same idea. So normally, we would write my mu I, the chemical potential, that's to be defined as total Gibbs free energy over the Ni at constant Tp and J not equals to I. So that's our typical understanding. Now, because we're looking at an ideal gas mixture, we know that for ideal gas mixtures, they don't have intermolecular interactions with each other. We can define our partial pressure of each species I as their partial pressure equals to mole fraction times the total pressure. So for ideal gas mixtures, we can write my mu I of each species. So let's use mu A as an example. So for ideal gas mixtures, we can write mu A equals to the pure mu A star as a function of temperature and the partial pressure of A. Only applicable for ideal gas mixtures. But that's pretty much as far as we're gonna go for this class. So we have our fundamental thermodynamic equations of an ideal gas mixture written as mu I equals to the standard chemical potential at some temperature T plus RT lowering partial pressure over P naught. Right, so this is the same equation we derived before, but now replacing that P final with the actual partial pressure of that chemical species in the reaction mixture. It sounds very abstract, but let's just look at an example question together. It's actually very straightforward. So for example, in this case, it's giving you this equation. Ask you to calculate delta G when the pressure of 3 mole of a pure ideal gas is isothermally decreased from 2 bar to 1 bar at 400 Kelvin. All right, I'm gonna ask you to give you some time to read the question. Right, so using the chemical potential equation we have to calculate delta G. So in this case, what do we know? We know that this is a pure ideal gas, so obviously it's one phase, it's all gas phase, it's one substance, pure substance. Ask you to calculate delta G. So what do we know for this system? We know that mu equals to Gm for this pure substance. What does that mean? So that means calculation of my delta Gm is effectively the same as calculating the change of my chemical potential between my final and initial stages. Right, so using this equation here, since we're talking about final minus initial, the first one will cancel out. So end up getting RT P final over P naught minus RT P initial over P naught. Or we can simplify it to be RT P final over P initial. And do we know what our P final and P initial is? Well, my final is 1 bar, my initial is 2 bar. So we can write that as RT ln 1/2. Right, so without actually looking at the numeric answer, this question, what's the chemical intuition behind this? Yes?
Did you forget to put ln?
Oh, yeah. Thank you for the reminder. There should be a logarithm function. Right, so without solving for the numeric answer, this is obviously a negative result. Right, we say it's negative, R is a constant, temperature is always positive, ln 1/2 is a negative number. So we're getting a very negative number here, talking about the delta G of the process. What's the physical meaning behind this negative delta G? So if we think about my delta G equals to delta H minus T delta S. Again, my delta H will be 0 since it's isothermal and ideal gas. And in this case, when we have delta G being a negative number, we're showing that delta S must be a positive number. And it also fits our expectation for the entropy change, right? We're reducing the pressure, so volume goes up for gases. When volume goes up, the total entropy will go up. So getting the number is one thing, but understanding what's the physical meaning behind that number is a different thing. All right, so this part is pretty much just an introduction into what is ideal gas mixture. How do we calculate my chemical potential of my ideal gas mixture? So the key equation we want to use for ideal gas mixture is the one given here. Now, in real life, our real gas is way more complicated than ideal gas, but the idea behind the thermodynamics is the same. It's just going to mathematically be way more complicated, but the process is going to be the same. So let's take one more step to use these things that we derived, to use this expression of chemical potential that we solved to now think about ideal gas reactions, right? So the first part is we mix our reactant together. We mix our reactant, like say A, B, and C together. Let's say in this case, we have a reaction, A plus B goes to C, or AA, BB, CC, or we can write it as 0 goes to AA, negative AA minus negative BB plus CC, right? So now we're looking at the chemical reaction in my ideal gas mixtures. So that goes to my ideal gas equilibrium. I think I only have time to get a very quick start, so I'll pick up on where we left over in our next lecture. So at the beginning, let's do a quick review on chemical reaction equilibrium. Right, so when we look at chemical reaction equilibrium, there are several things. First of all, by writing this double arrow, it's telling us we have reaction at equilibrium. And in here, again, just to remind you what we have, right? So this mu I is our stoichiometric coefficient. And my AI tells you that's my chemical species involved. What else do we know about reaction equilibrium? So to refresh your memory, when we talk about reaction equilibrium or material equilibrium in general, we have the sum of my stoichiometric coefficient mu, we have our chemical potential times the Ni goes to 0. So that's true for any material equilibrium that we care about. Now for reaction equilibrium, we went over to discuss what is my DNI in a chemical reaction, right? So the DNI of my chemical reaction is defined to be the stoichiometric coefficient times the extent of reaction, or this little sign C, right? Remember, we can solve for C, telling you, hey, C equals to negative 1.5 more. Basically means the reaction is going backwards, right? Cl can also be a positive number telling you the reaction is going forward. And the change of the number of mole of each chemical species equals to the stoichiometric coefficient times the infinitesimal change of my extent of reaction, so dC here. Right, so this is something we discuss when we talk about reaction equilibrium. So plugging this back into our DNI, what we end up getting is the sum of my chemical potential mu I times the stoichiometric coefficient times dC equals to 0. Right, just plugging that number for DNI. Now, in this new expression, we know that the infinitesimal change of my reaction extent, that cannot be 0, right? Even at chemical equilibrium, you always have infinitesimal movement of your chemical species. So if this term is not 0, it's very small, yes, but it's not 0. That means we must have the sum of my mu I Bi goes to 0, or the sum of my stoichiometric coefficient times the chemical potential must go to 0 at equilibrium. Or as a beginning, let's look at a specific reaction, right? So if we have a reaction like, again, AA plus BB goes to CC plus DD for an ideal gas reaction. Now at equilibrium, we have the sum of my stoichiometric coefficient times chemical potential equals to 0. So that translates into my stoichiometric coefficient CC, or C mu C, plus D mu D minus A mu A minus B mu B, but must equal to 0. All right. And since we're looking at ideal gas reactions, so the ideal gas chemical potential equation applies for our ideal gas reactions. Now, for example, in this case, if we're focusing on mu C, what we're writing here, so mu C must equals to mu C naught at some temperature T plus RT ln PC over P naught. All right. And what we're doing here is write out an expression of my chemical potential for each species, A, B, C, and D, in this expression, and write it for this condition that's true for equilibrium. So what we have here is writing the C mu C naught T plus RT ln PC over P naught plus D times mu D naught T plus RT ln PD over P naught minus A times mu A naught T plus RT ln PA over P naught minus B mu B naught T plus RT ln PB over P naught. And that sum must go to 0. I'm running out of time, but we'll pick up in our next lecture, starting from here, and come up with a definition for our equilibrium constant and talking about what does equilibrium constant related to our delta G of the reaction. I have posted my annotated notes, so if you don't have time to write this entire things out, it's up there. But nevertheless, hopefully I'll pick it up. I know I'm behind, but we'll see how fast we go. I might go a little bit quicker when we talk about the phase rule and just focusing on the phase diagram. But I'll have more information for you later on. But let's like just slow down and look at my equilibrium part, because this is something I really want you to get from this lecture. All right, I'll see you